Bismillah ar-Rahman ar-Rahim. I'm going to supplement this talk to the previous slide regarding electricity. I forgot to add it to the session. So as you can see from the first figure, the electromagnetic flow meter, which is made of an magnetic field, which is made of two coils. These two coils, B and A, creating this magnetic field, which is better to be alternating. It gives a better results. And we have through it a flow of, for instance, blood RBCs flowing through this blood vessels as a conductor. You see, so we have something moving in the magnetic field, which is perpendicular to it, and at the same time we have two adjacent electrodes C and D attached closely to the blood vessel to record the potential. So this is perpendicular to the magnetic field. So whenever blood flows through, we can record the average velocity. You see, you must put in your mind that you are recording the averaging velocity, because this blood vessel most probably is changed regarding its diameter and the type of flow. So this is the first thing that I forgot to mention regarding electricity, the electromagnetic flow meter, which is also used, of course, to measure the cardiac output. This is the second figure, shows the galvanometer, which is present in most of the anesthetic apparatus. It's made of a wire which is coiled in a way, as you can see, and jeweled on a bearing system. This bearing system is attached to a spring or something like a hair to control the movements of it. So this is being applied in a magnetic field, as you can see. And then whenever current goes, as you can see from the direction of the arrows, it makes the interaction occurs between this current present in the wire and the magnetic field moving a pointer on a scale, so it can measure the amount of current going through. So this is the galvanometer. This illustration shows the definition of volt, which is V equals W, which is WV on the upper part, and on the denominator we have the revision of the VA. So this is a way to remind this equation. So we have a circuit which is present, as you can see, from a direct current. This direct current creates an ampere of 4 ampere. I'm sorry, and this circuit creates a joule, a power, which in this example is figured out to be 96. So we have an ampere of 4 and a 96 watt. Whenever I divide both of them, I can yield the 24, which gives us the amount of volt, which is the potential difference. This is the configuration of the alternating current and the direct current. As you can see, the alternating current goes in two directions, creating sine waves, a positive item and a negative item. On the other hand, the direct current goes steady in one direction, as you can see. So we have two currents, the 240 volt and the 230 volt, which is the peak. The peak. Remember that this is the peak, it's not the average. So whenever I want to compare both of them regarding the beneficial of energy and heat, I go through what we call the RAM, which will show it now, the RAMs, which will compare both of them. Now, this is a figure showing, of course, the direct current, and this is the alternating current. And sometimes, in some circumstances, we have a combination of both of them. This figure shows what's the meaning of a RAM. RAM is a method to compare two types of current, alternating and direct, regarding its capability to induce energy and heat. So I want to compare. So to change this form of a sine wave of the alternating current to a direct current that looks like the direct current, I simply square this sine wave so that all the items will be positive. And after that, I gain the mean of it. And then whenever I get the mean, I apply the last thing is the square root of this mean, which will give me a figure which is called RAM. I can compare it with the straight line of the direct current. So this is the way to make the two types of current almost similar to each other. And then after that, we have, of course, the resistance, which it's by ohm, which is figured out by the difference between the potential and the current. These are symbols of the different components of the electrical items present, as you can see. And this is the difference between a resistor and an impedance. And this is inductor, a coil, and a capacitor, two conductors, and an isolator in between. And it's the battery, diode, a rectifier. Rectifier, I think it means that I am increasing the transformer makes the high volt to a lower, I'm sorry, a high current to a lower current. But rectifier is the reverse. This is the Woodson bridge, as we can see. Its aim is to measure, of course, an unknown resistance. It's made of 4 arms, as you see, R1, R2, till R4, and there's an electrical potential in this battery and an ammeter. Okay, of course, this system is called a null deflection method. What's the meaning of that? That it always the pointer is in the 0 point whenever R1 over R2 equals R3 over R4. These 4 arms, you see. So, for instance, I want to know an unknown resistance. Suppose the resistance of a thermometers. You know that thermometers are based on the change of resistance. I put it in this arm, and then this changeable resistor, which we call it rheostat, is changeable. So whenever I put this resistor in this circuit, this null deflection will be affected. So I come to this R4, I change it till the pointer goes back to 0. This difference can calculate, of course, the unknown resistance, which is R3. This is an isolator capacitor, out of the circuit of the patient. It's in the circuit of the electrical equipment of the diathermy, where there is, in case of there is a fault, this fault, suppose there is the detachment of the electrode and the patient is touching to an earthed equipment, and the current will go through this earthed way to complete the circuit. So this isolator capacitor protects the patient against electric push. It's not present in the recent books of Barbo. And this is the figure showing the defibrillator. Whenever the key word of the defibrillator is, of course, the capacitor, and we applied on both plates of the capacitor a volt of 5,000 volt. Here in this figure is written 8,000. So whenever I have a volt, this capacitor has a capability to collect this current. So the capacitor capability, which is named by Farad, equals the volt over the collecting electricity. So we have, whenever we have a 5,000, we have a capacitor in this defibrillator, it collects around 160 millicoulomb. You see, so of course the energy, we need energy to move this electrical amount quantity between the two plates of the capacitor, and to release it to the patient whenever we are in need of it. So this is the figure out of the energy. Whenever I want to gain the energy, I multiply the velocity, the volts by the amount of electricity which column. See, so when I multiply 160 and 8 or 5,000 volt, I gain, and I divide it by half, I gain what we know is, which is the 400 joule or watt per second. You see, of course, this is regarding the monophasic, the biphasic type of defibrillator. This is what we call the inductive capacitor coupling. You see, these are present in most electrical equipment, or most electrical equipment contain an inductor, which is simply a wire. This wire may be called or a capacitor. So all this create a potential. This potential may interfere with, suppose, as you can see, the ECG. So suppose this is the patient, this is the lamp bulb. So in between there is the air. So we are creating a capacitor. You see, as a matter of fact, this capacitor is capable to transfer this current, which is 50 hertz, through it. So this volt interferes with the diathermy. And as we said before, how can we do what we call a screening? The screening simply means that I am applying something made, suppose, of a woven metal around the electrode. Electrode, as we know, is made of silver chloride metal and an adhesive device, and then we put around it this woven metal. So whenever we have an interference current, it will go through this woven metal through the earth and will leave the normal ECG tracing not attenuated and being well traced on the screen. So this is a way, what we call screening. So this is a capacitor where it can interfere, and also an inductor of MR or whatever can interfere with the ECG tracing. This is the meaning of impedance. Impedance is a type of resistance, but it is affected or is correlated to the frequency. You see, and the symbol of it is, or the item of it is Z. So we have a resistance of impedance, of course, of the ECG and the skin, and of course of the equipment. We call it Z equipment. So we have two resistance or two impedance. Whenever I'm using a device such as ECG, it's better, of course, to have a high impedance of a resistance in such circumstances to diminish the attenuation of the signal. See, suppose the ECG has a high impedance than that of the equipment, it will definitely attenuate the signal. Whereas whenever this the equipment impedance is higher than that of the ECG, it will not much be affected. You see, so whenever, of course, sometimes the ECG is being loose or there is no proper gel to minimize this resistance, this attenuation, which will increase, which is much better whenever I use an equipment with high impedance. The last figure will show, of course, what's the meaning of the interference, as we can see from the figure. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.